Hey, it's me, Steve. It is September 27th, 2017. Time is 16:43, and it is 68 degrees Fahrenheit out for a change, as opposed to yesterday when about this time it was like 87 degrees and with a high of like 91. But I think we're done with that crap finally. But anyway, this is a Geo-Rant, and I want to talk about geologic structural features. Now, geologic structural features are very important because understanding how folds and faults and things like that exist in space is how we decipher the history of our planet, really, on a large scale. So first what I'm going to do is I am going to show you some, there are a bunch of basic types of structures. You have anticlines, synclines, domes, basins, faults, but I'm going to deal with just basically real quick the type of forces that form these things, and then I'm going to talk again about Baraboo. All right, so if you look at this here, I put the website on the bottom where I got this from. This is not my drawing. I did add the red arrows though. Okay, so when you have compressional forces, horizontal compressional forces, is when folding occurs. All right, you can get, synclines and anticlines, but you can also get those from tensional forces, which I'll get into in a second. But if you get faulting, what happens is you get a reverse fault. You get this down here. Okay. Now, tensional features or structure or forces, actually, that's when the crust is stretched, either through rifting locally or it's stretched as a compensation for being compressed somewhere else. And the type of faults you get from that are normal faults. All right. Now, you can also have shear tension, where instead of direct compression or tension, forces are acting at an oblique angle to one another, and those can lead to folds as well, but they can also lead to strike slip faulting, which is this one down here. All right, that covers that. Now, how do we recognize these things in the field? Well, I found this drawing online. There's a source down there, and the top is what you would see in the field. All right, that's what you would measure in the field. The middle picture, this is a block diagram. This part's the actual ground surface, and this is what it would look like in cross-section. But you make your measurements on top like you would here, and that helps you decipher what you have there. And in this case, this is a syncline. All right, so now we're going to get back to Baraboo. And as I mentioned before, Baraboo is like the Mecca of geology, and it is a very interesting place because in the late 19th century, early 20th century, we didn't really know. There's a big, I've talked about the issue of which is older, Baxter Hollow granite or the quartzite, but then we didn't even know if it was an anticline or a syncline. So some geologists like Van Hise of Wisconsin University, ended up being the president, and I think he has a hall named after him, started deciphering microstructures within the larger structure in order to determine that it was a syncline, and subsequent drilling has shown this to be true. All right, and so we figured out a lot about structural geology in Baraboo, Wisconsin. It wasn't figured out in the Rockies or in Alaska or in the Appalachians or the Himalayas or the Alps. It was figured out in the Midwest. So here is, this publication here is actually a USGS publication. There it is right there. I colored some of the things for you. And this is kind of like that cheap diagram I did in my other Geo-Rant about that quick one. This is a better diagram to show you what's going on. The orange is the Baxter Hollow granite, the yellow is older rock, the pinks are quartzites, the blues are slates, the grays are rhyolites, that red is dolomite and banded iron formation, and the green is the younger Paleozoic rocks. Now, as you can see, the Precambrian, which is everything that is not green, has structural feature to it. In this case, it's a syncline. All right, the Paleozoic is flatline. All right, So, and as you can see here, there are some question marks because this was done in 1991 and they weren't sure the extent of the rhyolite. They weren't even sure how old, that was still a question, which came first, the quartzite or the granite. And here, the yellow highlighted parts from the same publication, here they couldn't even figure it out. But if you look back at this, one of the things that were in there, this is why there's confusion, is because you see rhyolite class in the bottom of the Baraboo. But in the Baxter Hollow granite, you see quartzite, purple quartzite in it. So, and as I talked about before, it turns out the quartzite is younger than the Baxter Hollow granite, but not by that much. And also something interesting about the rhyolites in Baraboo Range, they're red and black. You almost never see black rhyolites. And if you just saw it sitting there and didn't know any better, rock in a box, you might just say, oh, basalt, and throw it out. But it's not. Remember, rhyolites are the extrusive form of granites, and the Baxter Hollow granite was likely the source, or partially the source, for these rhyolites, at least the red ones. The diorites could have been the source for the black ones. But remember the last Geo-Rant, I talked about the publication that the Wisconsin History Survey has, and I said it was circular 16. It was circular 14. I said I think it came out in 1976. It was 1970. And this is that publication. From this point on, everything's going to be from this publication with one exception, and I'll show you that. But this is the basic geologic map that was done in 1970 of the Baraboo syncline. And it's a huge area. The width of that map's about 13 miles, plus or minus a mile. I don't know, I didn't measure it exactly, but you can get this online to see. That way's north. And the red here is basically the Baraboo quartzite. Some of the red in the middle here is actually the dake. And that was another thing up until like last year. Some people thought the dake quartzite might have been, it kind of thrusted up, faulted for part of the Baraboo, but it turns out the dake quartzite is indeed its own quartzite. And part of the problem why people weren't very sure of that is because on top of the Baraboo you have slate, and on top of the dake you have slate. But it is its own thin formation. Sorry, excuse me. You gotta remember the Baraboo is thick. It's over a mile thick. It's this huge, thick deposit. But it is not the only deposit in Wisconsin that is a quartzite. Real quick, I'll go back to this. And then you got the Sioux quartzite in like west further, which probably correlates with it. See, these are just the quartzites in Wisconsin. And some of them, they have ages. And when they did this, they used structure, the existing structure and field relationships, stratigraphic relationships, to determine the relative age. And that's fine, because a lot of times that's all you have. And that's why structural geology is very important. Now, you saw the generic cross-section of the Baraboo syncline, but this is also from circular 14, and this is the several cross sections along the syncline. And as you can see, it's a lot more complicated structure than just a simple syncline. But the amazing thing about it is it does not have a lot of faults in it. And the couple faults they have here, like on this one, are estimated and may not actually be there. So there are no real massive faults known in the Baraboo. So after the Precambrian came and went, we had the Cambrian. Well, the late Cambrian, remember those flat-lying Paleozoic rocks I showed you? Well, here's what we think the paleogeography was of North America during the Cambrian. That line here is the equator. So North America was in the southern hemisphere, and as you can see, the star here is, or where is it? Oh yeah, it's right here. The star over here is the location of the Baraboo quartzite. And this long feature here is what we call the transcontinental arch. There is a Wisconsin arch too. It doesn't really show up here that well because it doesn't start to become really developed until the Ordovician and the seas transgress more. The dark blue here is deep ocean. The lighter blues are shallow, very shallow continental shelf to slightly deeper continental shelf deposits. So you can see there were a lot of inland seas at the time. All right, so why do I bring this up? Because during the Cambrian, the Baraboo Hills stood as islands. We know this because the Cambrian, basal Cambrian deposits of Parfrey's Glen Formation contain the Baraboo quartzite, and a lot of it, like Parfrey's Glen. I don't know if I've ever done a video for Parfrey's Glen or not, but anyway. So this is basically what it looked like in relationship. Your dark parts of your quartzite, the gray is water, and this is but the trade winds came from. And these hills are probably about 400 to 600 feet high. We're not sure of the depth of the water because it got deeper with time as the syncline, as the region subsided into the Ordovician, but the water was probably very shallow, maybe 50, 60 feet. And all around, basically, this gray areas where you started getting sandstone and conglomerate deposited, being derived from the actual Baraboo Hills themselves. So that was just a quick rant, and I hope you learned something.